Okay, good morning to everyone. And that was the Beatles' Naked, I believe, was the title of the album, and the cut is Get Back. So we are at the end of September. I felt like we probably should have played Neil Diamond's September Morn, about the last time we can do that for this year. We have a Lab 7 that you were to be working on over the weekend. And yesterday I spent some time with the output that Erlinda had, looking at that. I hope you've had an opportunity to work with the lab. You're down to 2 days left, and there's about 14 pages of output. I was out at the Sierra Hall 221 yesterday, spending some time out there. We had a meeting, and just again, can't encourage you strongly enough to go out there, spend some time there. It is one of the neatest places on campus to be at a computer. Help's available, and if you aren't utilizing it, you're giving up an opportunity that is really profound. We have a few questions on the lab, so what's the first question?
For the directions for number 6, it says use the first 30 non-repeating numbers from the random, just like the random sample.
Yes.
So if the first random number I have is 111, I wouldn't use that one.
Why would you not use it? 111 happens to be 3 digits that repeat. That's not what's referenced. If I have 111 and 15 numbers later I hit a 111, that is a repeating number. Otherwise, you should have in those 45, ideally, 45 numbers that are all different. Did you have any number that was listed twice? You have a rare set of random numbers. Most of the time, when we go ahead and we generate those 45 3-digit numbers, we will end up with at least one that is repeating. That is a duplicate. So maybe I should have used the word duplicate rather than repeating, since you ended up with a 111. Those are repeating digits, but that is not what I intended. Is that understood now? Okay. Anybody else have a question on that or related to Lab 7? How many of you have at this point generated your list of 30 countries? Okay, have you had a chance to look at your sample mean, your X bar? Okay, the question from yesterday, we had an interval. So the key is you're about 22. You have a standard deviation of 2. So if you were above, 24, now you're, okay, I'm looking upside down, so just leave where you are. 21.7 was our average for the 222 countries. So again, mu is 21.7, agreed? Let's go back through this one more time. By the way, it's chapter 11. The next chapter we're supposed to be looking at. Roughly 21.7 for mu. Sigma sub x bar, we argued, is sigma over the square root of n, where this is sigma sub x, this is mu sub x. It is true that mu sub x bar is just mu sub x. So the mean of these sample means, this distribution of sample means, is the same as the mean of your original population. Now we argued that we had a 10.9 something, nearly 11 if you round off. So we said this is about 11 over a 5.5. Roughly, well, I'll put here the square root of 30. It is just under 5.5. And so this became about 2. So if I take 2 of these under the empirical rule and add it to here, I'm at 25.7. Did any of you have an X bar that worked on it now? And I'm assuming that you at least found the mean and standard deviation. Do any of you have an X bar greater than 25.7? Okay. Let's go to the other side. Subtract 2 standard deviations. So that would put us down to what? 17.7? Did anybody get an X bar under 17.7? That makes sense. 95% of the time, we should be getting what? X bars in that range. Now, if I had 20 people with X bars this morning, we might expect what out of those 20? Okay, we still don't understand what 95% means then. We're arguing that 95% of the sample means, x bar, are contained in, that's a symbol meaning contained in, this interval, which is 17.7 up to 25.7. If 95% of the x bars should be in there, what's left not in there? 5%? Let me ask my question again. If we had 20 means, how many would you expect not to be in that interval? 1 out of 20 is 5%. One more time. If we took 20 means, then I would not be surprised to see 1 out of the 20 because 5% of the time I get x bars not in this range. So I'm not surprised with fewer than 20 of you with x bar at this point. I think we managed to get up maybe to 6 people who've done it now. I wouldn't expect any of you to have an x bar outside of that range. Now this relates to the central limit theorem. Again, what we're talking about, and this is content for the lab next week, and it is related to the next chapter following what we did in chapter 10 on sampling distributions. We're talking about the sampling distribution of the sample mean. And because, as we looked yesterday, the birth rates are not normally distributed, we have to depend on what is referenced as the central limit theorem, which basically says that even though our original distribution is not bell-shaped, it's going to tell us that x bar is approximately normally distributed. The larger the sample size, the better. Traditionally, 30 was the break point. Efforts to check this out in computer simulations have indicated that maybe 40 is a better number, but 30 has been traditionally used for about 80 years at this point. We'll stay with the 30. So what we're saying here is that x bar is big N, meaning normally distributed, with a mean of mu and a standard deviation equal to sigma over the square root of n, where n is the sample size. Now that's covered in chapter 11. We have, in essence, covered chapter 11 in our efforts for the last 6 weeks to talk about the distribution of x bar, which we have been doing since week 1. That's where you're headed. Okay? And of course, the question, is your sample representative of the population? And even if it isn't, I can use this whole idea and take just one sample from the population and use it to challenge a statement about mu. Now, where we're headed is to set up 2 statements, H sub 0 and H sub A. And they are going to be statements about the parameter. The parameter in question, mu, the population value. Now, we, in terms of the database we have, know that 21.7 is the correct value. But if I were basing this on information of, say, 10 years ago. Okay. Or 15 years ago. And that was when the Cairo Conference was done. And I stumbled across a reference to the Cairo Conference. And I wanted to look at whether or not the population of birth rates had a different mean. So at that time, let's say the figure was at about 29. And I'd like to show that 15 years later, it has changed in a significant way. Okay. Now, I would argue that it should have dropped. So I would have been inclined to say, well, I believe it's less than this. Now, I could take Erlinda's value from yesterday, and your X bar was about 22, was it not?
Yes.
22.1? Rounded off?
Yesterday.
What do you mean yesterday?
I had to recheck my calculations.
Okay, what is it today?
It's a 22.6943.
22.7. A day's difference. Okay, I'll take the 22.7, but it's still inside this interval. But in terms of this hypothesis, and by the way, one of the things that's been very intriguing, 15 years of data, sigma stays at about 11. Pretty darn close. So sigma x bar is usually about 2. Very consistent. So if I played the game here, I'm saying that x bar should be in what interval? Based on my null hypothesis that I believe to be true, mu x bar should be contained in an interval that is 29 plus or minus 4. So it could be as low as 25, could be as high as 33, correct? Playing the same issue. And let's just for a moment, Jennifer, slide over, pan over just enough to pick up this. Because if I contrast those, and I'll walk off camera, this was based here on mu at 21.7. But if this is what I believe is true, and I'm arguing that sigma is 11, so sigma over the square root of n is 2, then the interval that I should see the x bars is 25 to 33. Now, I take the 22.7. Is it in that interval? No. The mean found by Erlinda is inconsistent with what? Mu at 29. Because we don't expect to get the unusual. 95% of the time we should get values in here. So if I get a value outside of there, that happens less than 5% of the time, and we've argued what? Something under 5% is called significant. And therefore, I decide to reject this statement in favor of the alternative. And that's called hypothesis testing. Now, instead of setting up this interval, we typically just calculate a z-score. And a z more than 2 or less than minus 2 will be in the tail of the curve. Okay? And so we would argue that we have an inconsistent result here, and so we reject the null hypothesis. Now, if I take numbers from 5 years ago, not 15, things don't change very quickly. It's taken 15 years to drop about 7. That's about a half a unit per year. So if I look at last year, which may have been more up around 22, this is totally consistent with the 22. There has to be a difference to detect. Something has to change if you're going to find a difference. Okay? The greater the difference, the greater your opportunity to detect it. The smaller the difference, you aren't going to have much of a chance to detect it. So this happens to be chapter 11 that we're talking about, and it's related to what I'm asking you to do. But as you look at these numbers, keep in mind where we're headed, because we want to illustrate this idea of the central limit theorem next week, and that's where I need your sample means. And I'd like your sample means on a 3x5 card. And I have some cards up here if you need to get one, on a 3x5 card by Thursday. So I can put those on the website so that over the weekend you have the data that you can go ahead and work on Lab 10, with the idea that weekends are a good time to get a jump on the labs. Any question? That's Lab 7, well beyond what the question was. But are there any other questions regarding this? Okay. Yesterday we talked about probability. I'm going to come back to the text and look at some of the things we did. Remember, we talked about tossing a die, tossing a pair of dice, and then we tossed 5 dice. And we talked about the outcomes that we get, and I used the letter S for the outcome space. Now, you will find as you read in your text that David Moore is going to call this the sample space. The sample space is the set of outcomes. Other books call it the outcome space. So a sample space, outcome space are interchangeable. Now, there's an interesting problem that includes a diagram that's on page 252, if you'll be kind enough to turn there. 252. Now, depending on your background in geometry, you may or may not recognize this shape. As soon as I get the, okay, that's reasonably well done. Now, this is what is called a tetrahedron. You probably call it a pyramid. Okay, each side is a triangular face. There are 4 sides, as opposed to the die, which has 6 sides. So you have 1, 2, 3, and 4. By the way, rolling these, if they don't round off the points, hurts your hand more than it does with a regular die. Let's look at the picture again. Notice how the edges have been rounded. So up here at the top, it's not quite as sharp as it might be. A triangular-based pyramid. Now, those triangles are congruent to each other. One could lie on top of the other. A tetrahedron. So if I roll this, what are my possible outcomes? And by the way, the number that you record is the number face down on the table. So what would be your set of outcomes? I'm hearing very softly. 1, 2, 3, 4. Yes, it's 1, 2, 3, and 4. Those are your outcomes. So we would let S, as we go back to the board now, we would let S be the set containing 1, 2, 3, and 4, which is different than when we had a regular die, correct? We consider this a fair die. And by fair, what do I mean? Okay, not weighted. Can you give it to me in terms of probability? Okay, equally likely outcomes is what Alyssa said. Equally likely outcomes. Same probability getting a 1 as it is getting a 2, as it is getting a 3, as it is getting a 4. Now, I'm going to go ahead and create what is called a probability distribution. I'm going to tell you what x can be, and I'm going to tell you the probabilities for those values of x. Simply coding what was just stated. An x can be a 1, and the probability of the 1 is 1/4. An x could be a 2. And the probability is 1/4. An x can be a 3. And the probability is 1/4. An x can be a what? A 4 with a probability of 1/4. Agreed? I can have any of those values. Now, for any other value, what's the probability? A 0. So I've stated the values that x can have, and I've given you the probability. Now, we call this a probability distribution. It's also called a probability model. Every one of your probabilities is between 0 and 1. So we note every probability is between 0 and 1. And furthermore, we note that the sum of the probabilities is 1. Now, I could have said p sub I, if you wish, for the different probabilities. Okay? So I have the probability defined for each value. Now, this is called a discrete probability distribution. Okay, so we're referring to a probability distribution. And this one is discrete. Now we're going to contrast that to a continuous probability distribution. Now to find the probabilities for any value of x here, I need the table. I need to know what the model is for a discrete. For a continuous one, I'm going to draw a diagram for you. This is one we talked about earlier. Let's see about how long I'd like to make that. Let's go to here. And what I'm going to do, let's see, make that the center there. And so, I'm going to come up. Let's see which way I want to do it. I think I'll do it this way. Okay, 7.5. Now I'm trying to make this to scale. This is 0, this is 1, this is 2, and this is 1. Now that is a triangular distribution. Now my density curve is that line. Can you give me the equation of the diagonal of this right triangle? Anybody?
Y equals -1/2x.
Y is going to equal something times x. I'll agree with you there. And the question is it positive or negative? I'll agree with you the negative. And so how do you get the slope? Otherwise, as we look at that, slope is what? As a reminder, rise over run, correct? So what Sean is observing is you have a run of 2. As you go from this point to this point, your run is 2. That's where he gets his denominator. And the rise was a drop of 1. So that's a good start, but not the equation.
Plus b.
Well, plus b, but what is b? What is it obvious that it b is? No. 1. B is your y-intercept. And this line's going through 1. Agreed? So, we'd argue that I have y equals -1/2 x plus 1. That's my density curve. Now, for a continuous probability distribution as opposed to discrete, I have to give you the equation of the density curve. And now, what are the possible values of x that I can have? Anything from 0 to 2. Whereas the probability that x equaled 2 here was 1/4, there's no probability associated with a single point in a density curve for a continuous random variable. Here, when x was 1, slide just a bit if you could, Jennifer, tweaking that. When x was 1, probability was 1/4. When x is 1 here, probability is 0. Now when I take this particular result and I can say the probability that x is, let's say, less than or equal to 2, then I add these two together and get 1/2. I can do an interval here. So for example, I can set this at 1 and ask, what is the probability that x is greater than or equal to 1? And I want that area. True? How would I find it in this particular problem? Using the area of the triangle I've created. So the triangle has a base of 1. Remember, the area is 1/2 the base times the height. So if I look at that formula and I look at the base is 1. So I'm going to have 1/2 times 1. Better make that an x, I think, for what I'm doing here at the moment. Hate to do that, but let's keep it just in terms of the normal operations and the symbol times. What is the height? Then how do I get that? I could substitute into the equation of my line. I could use similar triangle argument out of geometry. Okay. But let's use the algebra. X equals 1. I have minus 1/2 times 1, which is minus 1/2, plus 1, which is 1/2. So the ordered pair here is 1, 1/2. I just substituted x equals 1 into that equation. So what is the height of that triangle I have with the diagonals going through it? The height is 1/2. Agreed? So what is the probability now of saying that x is greater than or equal to 1? Or if you will, I could say the probability that x is between 2 and 1. 1/4. Now for a continuous probability distribution, the area under the density curve has to be 1. And the only questions I can ask involve an interval, not a single point. Contrast these two, discrete and continuous. Okay? Now note the similarity. The sum of all these probabilities have to be 1, and the area underneath this triangle has to be 1. And I hope you realize that if its height is 1 and its base is 2, 1/2 times 1 times 2 is 1. We meet the conditions. Continuous, discrete. Bell-shaped curve, continuous or discrete? That's not a rhetorical question. I expect an answer. Bell-shaped curve, you know the density curve equation. We've done that. Is that a discrete or a continuous probability distribution? You should be answering continuous, because the area under that curve is 1, and all we worry about is finding probabilities in an interval. Plus or minus 2 standard deviations in each side of the mean, 95%. Continuous random variable. Okay? Now I'm going to come back to the diagram. I started this by talking about what we see in the document cam. A tetrahedron. Now this problem about the tetrahedron is going to involve a discrete probability distribution. And what they do is they take 2 of these dice and toss them. How many different pairs do you have in your sample space, the outcome space? Yesterday, we said if you had 2 regular dice, you would multiply 6 times 6. And with 6 sides in each die, you just used a multiplication principle. 6 times 6 is 36. When we had 5 dice, you said 6 to the 5th power for 7,776. So the 16 that one of you said is a correct answer for this die. 4 times 4. Yesterday, we talked about the sum of the pips. Could be between 2 and 12. So what would be the sum of the pips for this particular probability distribution? You could start out with a 1, 1 as your lowest, which would be a 2, and what's your highest possible value? An 8, agreed? And just like we did on the 36 pairs, you could look at these 16 pairs and you could give me the probability for getting X at 2, then 3, then 4, 5, 6, 7, and 8, and you can give me the probability distribution. And that's exactly what that problem asks you to do. Play Yahtzee with these dice. How many separate 5 tuples will you have playing Yahtzee with tetrahedrons? What to the 4th?
4 to the 4th.
Haven't heard it right yet. It's not 5 to the 4th and not 4 to the 4th. How many dice are you going to roll? 5 dice. It's not 5 to the 4th. It's 4 to the 5th. 4 times 4 times 4 times 4 times 4. 4 to the 5th is 2 to the 10th. By your head again. 4 to the 5th is 2 to the 10th, because 4 is 2 squared, 2 to the 5th, so 2 to the 10th. And 2 to the 10th is 1,024. 32 squared. It's a lot easier to do 1,024 separate entries than 7,776. But now I'm going to ask you a question with this game of Yahtzee with pyramids. Something the Egyptians might do. You're going to play Yahtzee with 5 pyramids. What's the probability of a Yahtzee? How many ways can I get a Yahtzee with these pyramids? Yahtzee's still going to be all the numbers are the same. So what are your possible numbers that have to be the same? All 1s, all 2s, all 3s, all 4s. Can you get a Yahtzee in any other way? You can't have all 5s because there's only what? 1, 2, 3, or 4. So how many ways can you get a Yahtzee out of the 1,024? 4. 4 is 2 to the 2nd. So you have 2 to the 2nd over 2 to the 10th, which is 1 over 2 to the 8th. That's your probability of getting a Yahtzee with these 4, or these 4-sided dice called pyramids. Is there any question in that? That was just a playback of what we did yesterday talking about Yahtzee. And notice I never once used a decimal. Didn't intend to. Any question there? Okay, let's take it one step further. What's the probability of not getting a Yahtzee with these pyramids? Wow, that's soft. Try it one. Was that you, Daniel?
Yeah.
Okay, louder so I can hear it, and I'm only 6 feet away.
1,020 over 1,024.
Yes, with authority. 1,020 over 1,024. That's the probability of not getting a Yahtzee. Couple 9s still after the decimal. Okay. We could play Yahtzee with other regular polyhedra. Okay, could be fun. The pyramids are about the simplest version I can give you that doesn't get too complicated. Okay, so we need to look at some rules. Page 253. We did these yesterday. This is just an effort today to kind of rewind the tape, get back to where we were yesterday, and I'm not getting this so it looks nice and regular, but we'll try with this. Okay, let's see what we've got here. Probability rules. This is page 253. The probability, called P of A, of any event A. What is an event? Coming off there for a moment. Give me a definition, some working definition of an event besides the Beatles playing somewhere. That would be an event. But I want something in a mathematical sense. We say that an event is what related to S from yesterday? An event is going to consist of outcomes. So outcomes are involved, but that's not the word I want. It is a particular set of outcomes. What kind of set? Subset. There we go. An event is a subset of S. Okay. So an event is a set, but more particularly a subset of the sample space. And of course it satisfies a particular result that I had on the board just a minute ago. When we referenced the board, the probability is between what? 0 and 1. Now, this next step that you see on the monitor is really saying the sum of the probabilities equals 1. The probability of the sample space is 1. Now, if you have equally likely events, the number of elements in S is the same as the number of elements in S. Remember my statement for the probability of A? Equally likely outcomes, probability of A is the number of elements in A over the number of elements in S. So that hopefully makes sense to you. Here is the addition rule that we had yesterday. Now I made an observation for you about the probability of A or B being the probability of A plus the probability of B, and I said what had to be true for this to work. What about the intersection of the sets A and B? Close, not 0. Not our relationship, because we're talking about sets. Operations with sets. What kind of operations are we allowed with sets? I gave you 2 yesterday. What 2 things can you do with sets? I say set A, set B. What could I do with A and B? We're digging. This is called digging for data.
It could be
Okay, a union of sets. A union B. What else can we do with sets? Besides finding their union, we can find their intersection. And I said this particular formula was based on A intersect B not being 0, being the empty set. There's a difference. It is the set that contains nothing. There's nothing in common with those 2 sets. So back to the document cam. So this statement is verbalized as disjoint events. They have nothing in common. Disjoint. A intersect B is the empty set. Lastly, the complement rule. Now I said tilde A meaning not A. You can say A does not occur, as you can see in the screen, but it's 1 minus the probability of A, and it is how we deal with Yahtzee and not a Yahtzee. The back door. the complement rule. Now, those are the rules we have up to this point. We're going to modify them a little bit in another chapter we're going to cover, which is called Chapter 12, which is Probability Part 2. But we're still working on Probability Part 1. Okay. We talked about the discrete probability distribution, and we're on page 255. A model, a probability model, at the top of page 255 is called discrete if we have a finite sample space. Well, what we've been doing with the board, where x could be 1, 2, 3, 4, that's finite. If I take the continuous value, shouldn't say value, the continuous model, I said x could be anything between 0 and 2. There are infinitely many possibilities between 0 and 2. But note, as we go back to the book, we assign probabilities in a discrete probability model. We list the probabilities of all the individual outcomes. Okay? The probabilities must be numbers between 0 and 1, and they must have a sum of 1. And the probability of any event is the sum of the probabilities of the outcomes making up the event. Now that's a slightly more general statement than what I had yesterday. Okay, so if we look at what I have on the board, and we're going to go back behind me now, Jennifer, to where I had S equals 1, 2, 3, 4 as a set, just coming back there with camera 2. When we looked at this, we assigned the probabilities because of what we know about rolling a single die that's four-sided. Okay? And if I want the probability of an event like the event that I have an even number, so that means a 2 or a 4, I simply add these two probabilities. Okay? But I could have said, since my event E contains the elements 2 and 4, and since they're equally likely, I could have said the number of elements in E is 2, the number of elements in S is 4, and I could have had my 2 fourths that way. But that only works when I have equally likely outcomes. Now I want to contrast that to something called Benford's law. This is a very fascinating result that I think you will find maybe counterintuitive. Benford's law. You were an accountant working with a company, and you ask to see their invoices because an audit is going to be done. So an audit's being done of an accountant. So we go through the invoices. And we're trying to determine if there's some kind of fraud. Okay. Enron comes to mind. I mean, this has been the kind of thing that Wall Street was consumed with not too long ago before the events of the last week. Okay, in which yesterday, I hope you realize, you basically lived through an historical moment. What was the drop of the Dow at its worst yesterday? 780 points, because a $700 billion package failed in the House. I found that interesting, about 1 point per billion. So roughly a 780 point drop, the highest drop ever recorded, and that includes 1929. Okay, historic moment. Benford's law. Okay, I'm going to come back center here, Jennifer. Benford's law relates to this problem that we're looking at. It's right below the definition we were just observing. As I say, I think you'll find this counterintuitive. Here are the leading digits of an invoice, and here is the distribution of the leading digit of invoice. There is a 30% chance it's a 1. Now I'm going to slide over. You can see what's happening, but let's go to the 9. Not even 5% chance that it's a 9. It's counterintuitive, but it seems to hold. So if I look at invoices, the chance of it starting with a 9 is only about 5%, but the chance of it starting with a 1 is about 30%. Now, if it were a discrete uniform, where have you seen the phrase discrete uniform in the last 24 hours for most of you? Who just let me know that you had generated 45 numbers between 1 and 222 using stack graphics. What was your selection to do that when you were given the choice of probability distributions? Did you use the default normal? What did you use? Discrete uniform. That means that every piece of data you wanted, which was a number between 1 and 222, have what probability of occurring? 1 over 222. Equally likely outcomes. Uniform distribution. A discrete uniform distribution. And if somebody had told me before I discovered Benford's law in a textbook that I was going to be doing an audit and looking at invoices, I would have fully expected a what? Uniform distribution. A 1/9 probability, which is roughly 11%, for each of the values from 1 to 9. Now, ask you this question. What is the probability that I will get a leading digit of 2 or less on invoices? So let X be the digit I get. The values for X are 1 through 9. So what's the probability that X is less than or equal to 2? Okay, Daniel's doing his usual very soft response. Okay, he's increased the volume a little bit. Could you hear it, Jennifer? Still couldn't hear it, and the microphone is only about 3 feet from his chin. His answer was correct. It's 0.477. Let's look at the document cap. You add what? The 0.301 to the 0.176. You just add those two probabilities, and you have your answer. Roughly 48% of the time, I'm going to get a 1 or a 2. That's nearly half. 50% of the invoices to the nearest 10% will be at a 1 or a 2. So what happens if I go into a company, look at the invoices, look at a couple hundred invoices, and find that 20% are between 1 and 2? Don't you think I challenge the credibility? Somebody's cooking the books. They think there should be a uniform distribution. They cook the books so everything comes out even. Benford's law says if it's a really non-cooked set of books, of invoices, that you'll have roughly 47% of the invoices starting with a 1 and a 2. We used another theorem. The Benford's law isn't a theorem per se. We used another theorem that I said could be used in an audit. What was that theorem? Hint, it was in box plots. It was on page 5-4 or 5-3 of the lab manual. Starts with the letter C. Not central limit theorem. That was a good start with C. It's a theorem. That's one of 2 correct answers that you might have had.
Chebyshev's theorem?
Chebyshev's theorem. because you are guaranteed what? At least 75% within 2 standard deviations, no matter what. And so if you got a 50%, you'd say you cooked the books. That's an audit tool also. Okay, Binford's Law. Now, Binford's Law is important to the extent that it gives you a non-equally likely set of outcomes to contrast to what we've been dealing with, rolling dice. You will have some problems with Binford's Law. Okay. The continuous probability model, compared to the discrete we just talked about, is on page 257. And this assigns probabilities as areas under the density curve. So again, that's just like the triangle I just drew. And the area under the curve. Now, curve is a very generic phrase there. Now, the area under the curve and above any range of values is the probability of an outcome in that range, which is a somewhat difficult sentence for me to interpret. If I want the probability that x is between a and b, I look for the area under the density curve. Curve, a generic term, because a line in that sense is a curve. Back to camera 2 on the triangle, if you would please, Jennifer. We're back to the triangle. This is my density curve, which happens to be a linear function and is not curved in the usual sense of the word like a bell-shaped curve. But that's my density function, the equation of the density curve, and that's a continuous probability distribution. Back to the document camp. And the area underneath that density curve has to be 1. Okay? So that covers page 257. The example given on 258 is one we did before. This happened to be a uniform, continuous, now notice the difference, uniform and continuous, because the height of that square is 1, the base of the square is 1, so the area is 1. And so finding the area between 0.3 and 0.7 on the left side of that diagram is just finding the area in the green rectangle. Coming off there, there's a better one related to what we just did, a little different triangle. This is an isosceles triangle. The triangle I had on the board was a right triangle. This is fundamentally the same problem. Unfortunately, when you look at the density curve, you have to break it into what? 2 pieces. The density curve to the left of 1 is an intercept of 0, so this is y equals 1/2 x. Okay? Go 2, we're at 0. Come over here to 1, so you went up 1. I should have said y equals 1x, not 1/2. I was thinking again of the right triangle. So y equals x for here. But in this case, the slope is what? -1, and its intercept is going to be up where? At 2. So we have to parse this out as 2 functions, and that is a continuous probability distribution. Of course, at the top of the page is the infamous bell-shaped curve, in this case, what we're calling the standard normal curve, centered at 0 with a standard deviation of 1. Okay? So that is what we've talked about earlier. And finally, without getting into personal probabilities, which is the last part of this chapter, a random variable, an RV, okay, is a variable whose value is a numerical outcome of a random phenomena. That's sort of chasing rabbits. It's a variable and it's random because you get your values from randomness. Now, we get The probability distribution, and that's the important part, the probability distribution requires that you tell what x can equal and the probability for each of those values. So a probability distribution could be called a what? Instead of distribution. If I give you x and p of x for each x, and I have a table, what's another name for a table like that? Okay, it's discrete. Go further. Think of algebra. I give you x and y, and I have a set of x and y's. What do we call that set of x and y's? I was hoping you would think of the word function. A function is a set of ordered pairs. For each x, there is what? Only one y. That's a function. So a probability distribution could be called a probability function if you want to think of your algebra. Now, the personal probabilities that are discussed on page 261 are oftentimes things that we just get in our head and difficult to defend. The key phrase here on page 262, they reflect a person's individual judgment of how likely the outcome is. Or another way, how optimistic you are. Okay? So you ask, well, how well do you think you're going to do in this test? Well, I think I've got about an 80% chance. You didn't study. You have done no homework, no labs, and watched no lectures. You come into the test and ask the same question. What do you think your chances of passing? Well, about 80%. You have to have a profound belief in divine help to believe that you still have that chance given those circumstances. We tend to overestimate the probabilities of success when we're doing it out of individual judgment. Difficult at times to verify. I always loved the report for the weather back in Colorado when I was in a doctoral program. The chance of showers today in the summer are 40%, because about 40% of the time you get a thunderstorm in the afternoon. You don't have to be a meteorologist to make that kind of statement. Or I love the one where you put your head out the window and say, hey, it's raining. Chance of rain today is 90%. Individual judgments. You can now do Chapter 10 homework. And believe it or not, you could probably do Chapter 11 homework. But tomorrow I will talk about Chapter 11 a little bit more. And then I'm going into Chapter 12, which is an effort to generalize Chapter 10. And with that, we are going back to the Beatles. And what is your choice as we close?
Don't let me down.
Don't let me down. Oh, wisely chosen. Have a good morning.